Good morning, viewers. Good afternoon and good evening, wherever you are watching us from. This is your online tutor, Steve Gitau. We are on the YouTube channel at Steve Gitau 3660, and soon we shall be having our materials on a website, Educational Resource Center. So welcome to our lesson, and today we shall focus on calculations in electrochemistry. Basically, in electrochemistry, we focus on Faraday's first law, and this law enables us to calculate the mass of substance, maybe a metal deposited, or the mass of product, could be a gas produced. So the first focus there is calculating the mass of a product. Number two, Faraday's law enables us to determine the charge on the ion, which is unknown. Maybe a metal ion that was discharged. And then number three, we also look at the REM of maybe the metal which was discharged. And of course, we cannot miss other minor calculations like the time and the current. Welcome to this lesson, and let's get started. In question number 1, we evaluate what is ideally first law of Faraday in electrolysis. We call it Faraday's first law of electrolysis. How does it state? It states that the amount of product in terms of maybe the mass, it could also be volume if it is a gas, but that is a measure of the amount produced during electrolysis is directly proportional to the quantity of charge, the quantity of electricity passed, to the quantity of electricity passed. So that is very, very important, that during electrolysis, the more current you pass, the more time you take, is actually a measure of the quantity of electricity that has been passed. And that means the more the electricity passed, the more the product at the end of the process of electrolysis. For us to understand that, we shall look at 4 main questions. In question number 1, we look at a situation here. A student silver-plated her spoon by passing 2 amps or 2 amperes of current for a time of 2 hours through a solution of silver bromide. So silver bromide was the electrolyte. Calculate the mass of silver deposited. So naturally, we expect the silver ions to be deposited at the cathode, since they are positively charged. Now, for us to solve this question, and the item we are looking for is the mass, we shall need to express Faraday's first law in terms of the symbolic equation, where we say the charge, the quantity of charge is abbreviated as Q, and it has the particulars I for current times the time, whereby we have to note here that the time should be in seconds. So looking at our time here, it is given as 2 hours. 2 hours, we convert it to minutes. multiplied by 60. We convert those minutes to seconds. We multiply by 60, and students, key that on your calculator and let us know what we obtain from that. So we have 2 hours converted to minutes, minutes converted to seconds, and that comes to be 14. We can convert that very quickly. That will be 3600 multiplied by 2, and that gives us 0, 0. That is 12, 7. These are seconds. So we bring in this here, and we shall have the calculation. Therefore, the current was 2 amperes multiplied by the time now, 7200 seconds, and that comes to be 14,400 coulombs. So this is the quantity of charge that was passed. Now, let's look at the equation. Practically, what happened in the electrolysis? We see that the silver ions with a single charge received an electron, and they were deposited as a silver atom. So what does this lead us to? It leads us to see that where we show an electron, quantitatively, we are referring to 1 mole of electrons. 1 mole of electrons is equivalent to 1 Faraday. And 1 Faraday, which have been given, is equal to 96,500 coulombs. What does that mean? It means that 1 Faraday was able to deposit theoretically an amount 108 grams, whereby the RAM of silver is 108. It means that 1 mole of silver weighs 108 grams. And this is the calculation therefore. So we can make inferences whereby this 1 Faraday is going to be equivalent to 96,000 coulombs. So the question is, during this electrolysis, if 96,500 coulombs deposit 108 grams, what about the quantity of electricity that we practically passed of 14,400 coulombs? How much did it deposit? Cross multiplying, we get this is equal to 108. 108 times 14,400. Divide that by 96,500. So, viewers, on your calculator, let us punch that and see how much we get. From the calculations, we get that this comes to be 16.116 grams. And so that means, you can see, we were not able to deposit the whole 1 mole because our amount of charge was less than 1 Faraday. It was below 96,500. So we are now seeing the implication of first rule. The greater the quantity of electricity passed is proportional to the amount of mass in terms of grams of the solid that we are producing. In this case, we are producing silver. So this will be part 1 of what we say Faraday's law is used in determining the mass. Viewers, put that down on your notebook and let us move to question number 2. In our question number 2, we are having when a current of 0.8 amperes was passed for 5 hours through an aqueous solution of a metal Z. So the metal here is unknown. We see that 2.85 grams of the metal were deposited. So that is our product. The metal Z is our product. Determine the charge. We are required to determine the charge of the ion on metal Z, given that 1 Faraday is 96,500 coulombs and the RAM of Z is 52. So how do we tackle this question? We have the freedom to tackle it from very many perspectives. First, we may determine the quantity of electricity passed. So we can have Q is equal to IT. The quantity of charge passed is directly proportional to the current multiplied by the time that current passed through. And that gives us 0.82 amperes multiplied by the time is 5 hours, which is going to be, we can convert that to minutes multiplied by 60, multiplied by 60 to make, to convert the time to seconds. So viewers, on your calculator, let us punch that and see what we get out of that. From the calculator, we are going to get 14,760 coulombs. Now, we move to part 2, and this part requires our understanding. Let us digest the question. This mass was deposited when this current was passed. We need to have a relationship with the RAM. In our previous question, we said RAM stands for the mass of 1 mole. So we can use this value here to know how much would 1 mole require to be deposited in terms of the current. How much current, therefore, would 1 mole require? What do we mean? That 2.85 grams of Z required 14,760 coulombs to be deposited. Now, what about 1 mole, which weighs 52 grams? 52 grams of Z would therefore require, we do the cross multiplication, 14,760 multiplied by 52 divided by 2.85. So viewers, key in that on your calculator and let us see how much charge would that require. What are we getting? We should be able to get approximately 630.19 coulombs. 0.19 coulombs. So this is the amount of charge required to deposit 1 mole of Z. Now this step is very critical because we need now to show it in equation form, that Z with a charge which we do not know, N positive, required some amount of electrons to be deposited and to get Z in solid form from its solution, from its aqueous solution. So this will definitely be N in a number because the charge cancels out. the negative and the positive. Now, at this point, we are going to say that quantitatively, all this charge equates or amounts to 289,630.19 coulombs. 0.19 coulombs. So for us at this level is to determine how many Faradays are this. So from our earlier, or what we are given that 96,500 coulombs is equal to 1 Faraday. What about 289,630.19 coulombs? How many Faradays are those? So we do the division or the cross multiplication. 1 times 289,630.19, we divide that by 96,500 coulombs. And what we get? Kindly key in. I would like to make this session as interactive as possible. Key in and let's get a value. I expect that you get 3 Faradays. 3 Faradays. What is the significance of that value? It means that all this charge N is equivalent to 3 Faradays. And 3 Faradays is equivalent to 3 moles of electrons. 3 moles of electrons. And what does that mean? It therefore means that the Z with a charge here is being neutralized. Is being neutralized by 3 moles of electrons. 3 moles of electrons which are negatively charged require 3 moles of positive charge for complete neutralization. That means the N is equal to positive 3. The charge on Z is a positive 3. And that is what we are looking for. We are required to determine the charge on the ion of metal Z. So in this question, if we were to mark and see what were the key areas, we would take that this is very crucial. Writing the formula is always going to earn you a mark, and the subsequent substitution gives you half a mark. Now, this relation, whereby we relate the mass deposited to the quantity of charge supplied to earn the quantity of charge for 1 mole, should give us half a mark. Now, being able to bring down the equation earns us another half a mark, and now this calculation here will earn us half a mark to develop this, and the final answer another half a mark, and that gives us 3 marks for that particular question. Well, in different forms of evaluation, the marks distribution may vary, but these are the key areas that we may be required to show. Indeed, we are saying, if we move back slightly to question number 1, which we had solved earlier, you realize that the writing of the formula is very important. It earns you 1 mark. The value that we obtain gets us 1 mark. The equation will give us half a mark. And how we relate that equation to determining the mass, this will give us half a mark. And so far we have done 1, 2, and the final answer may be worth 1 mark, and therefore 3 out of 3 can avoid. These are short answer questions which learners are supposed to calculate, and so far we have seen 2 areas. The first being calculating the mass deposited, and that is calculating the mass deposited, and in part 2 we have seen calculating the charge. Let us prepare for question number 3 and number 4, whereby we shall look at the RAM and other variables like time and the amount of electricity passed. Time, mass, amount of electricity passed, we shall look at them in question number 3 and number 4. In question number 3, we are looking at when a current of 1.2 amperes is passed through a molten oxide of a trivalent. That word is very key. An oxide of trivalent metal M for 75 minutes, 0.54 grams of the metal were deposited at the cathode. Calculate the RAM of metal M. So in this question, we are seeing the third application of the calculations on first law of Faraday for electrolysis. That is determining the RAM. Now let's digest this question. The first thing is we shall be able to link these two so that we are able to get the quantity of charge passed. And as we had said earlier, you are free to tackle the question from either angle. There is no defined criteria on where we should start, but we should be able to piece all the items together. So number 1, let us calculate the quantity of charge passed, and that requires Q is equal to IT, which comes to be 1.2 amperes multiplied by the time in seconds. So 65 minutes converted to seconds will be 75 times 60. And key in that on our calculators and let us get a value. What value in terms of coulombs do we get? From the calculator, I'm able to get 5,400, that is 5,400 coulombs. So this is the quantity of electricity that was passed. Now, part 2, we ask ourselves, when we pass that electricity, what happened to it? What happened to it? So we need to visualize the electrolysis, say in terms of M, which is trivalent. Its formula with the oxide would be M2O3. So this is what was decomposed to yield some M and some oxygen gas. It was broken down. So if this was broken down to 2, then we have 3 here. We balance so that we may get a clear picture of what happened. And that is what we are talking about. This was melted down. This was melted down because we are having the molten, but this is not the calculation which we are focusing on. The calculation which we are focusing on will involve M, which is trivalent, requiring some charge here to be deposited. And at this point, we look at the question. What is the question giving us? That during this reaction, if it is ideally trivalent, then we shall require 3 moles of electron to deposit 1 mole of metal M here. Now, let's look at the values. The values are that when this quantity of charge, which we are given as 400 coulombs, they deposited this mass 0.504 grams. So we can do this kind of a relation, whereby if this quantity deposited this much, what would be the effect of 3 Faradays? From theory, 3 Faradays are required here. And it is we can approach it in that dimension, or we can ask ourselves, how many Faradays were this? So if 96,500 coulombs are equivalent to 1 Faraday, what about 5,400 coulombs will be equivalent to how many Faradays? And that will give us the calculation 1 times 5,400 divided by 96,500. So viewers, key in that on your calculator and let us see what you get. So on my part, I am able to get 0.05596 Faradays. What is the meaning of that? That for us to deposit this mass, these were the Faradays required. Now, the question is, this 1 mole of this required 3 Faradays. So with that we can argue out if 0.05596 Faradays deposit 0.504 grams. What about these 3 moles of electrons represent 3 Faradays? How much would 3 Faradays deposit? So we got to that level, and 3 Faradays would therefore deposit how much? 0.504 times 3 all over 0.05596. So viewers, on your calculator, let us punch in that one, and I want to redo that again. We are saying that this metal is trivalent. It has a positive charge of 3. So it requires 3 moles of electrons to deposit 1 atom, or not 1 atom, but 1 mole of it. However, in the experiment, we did not have 3 Faradays, but we had 5,400 coulombs, which deposited this much. This quantity of charge in Faradays are equivalent to this one. So these Faradays deposited this. What about the 3 Faradays that we would require to deposit 1 mole? And 1 mole is what's going to give us the REM. So from the calculation, I want to believe that you have keyed in, we are getting 27.02 grams. So the REM of metal M is 27, we can round it off to 27 grams, or due to isotopes, 27.02. Now let us put that in form of an equation so that we can summarize the question. So we are seeing M, the charge of 3, requiring 3 moles of electrons, or 3 Faradays, so that we may deposit 1 mole of, this is molten, so liquid, 1 mole of metal M in solid form, and that is 27.02 grams. So this is how we derive it. 3 Faradays deposit 1 mole. How much is 1 mole? And that gives us the calculation. So in this kind of a question, the students are free to leave their answer as they got it, as 27.02. Now, we can mark this question, and so we have half a mark for that. We look at the approach, the obtaining the number of Faradays is very important. Getting the number of Faradays and relating it to the mass, we get another half mark, and being able to obtain this final mark, you can give 1 mark. So in this case, we have 3 out of 3 for that question. So viewers, we've gone through this systematically, and we are saying at this level, a learner may even decide to switch and work with the coulombs in terms of how many coulombs are there in the Faradays. Let's look at question number 4. Question number 4. In question number 4, we have a similar question. Indeed, let this be a test question. So you can pause on the video, work it out, and then play back and see if you are able to get it right. How does the question read? The question reads a mass of 1.24 grams of a divariate. A divariate metal was deposited when a current of 6 amps or 6 amperes was passed through the solution of metal sulfate for 12 minutes, determining the REM of metal that was deposited. So viewers, pause on the video, work it out through with the area approach, and see if you will be able to assess your understanding correctly. Now, let's get moving. We may give this metal the symbol P. So, being divariate means it has a charge of 2. Divariate. The previous question was trivariate. So, it requires 2 moles of electrons to be able to deposit 1 mole of the metal P. Now, let's feed in the values. We had the quantity that was deposited, 1.24, when this happened. What was the quantity of charge passed? So this comes to be 6 amps times 12 minutes would be 12 times 60 in terms of seconds. And that comes to be what value? Kindly key in on your calculator and let us have this value. So we are going to get, that comes to be 4,320. 4,320 coulombs, capital C. Now, what is the relationship here? How do we relate it in this case? We can do a relation and say that the 43,220 coulombs deposited 1.24 grams. Deposited 1.24 grams. What about 2 Faradays? So at this point, we can come in and say 2 Faradays is equivalent to 96,500 coulombs times 2. This is what we are provided here. So how much would that deposit? So 2 times 96,500 coulombs would deposit how much? We calculate that as 1.24 times 2 times 96,500. We divide that by 4320. So viewers, key in that so that you can say, these 2 Faradays here, how much in terms of grams will they deposit going by this area working? Key in that, and I want to believe that you are going to get 55.3981 grams. It is acceptable to leave your answer as it is on the calculator without having to round off. Indeed, this is accurate without any rounding off. So with that, what is the meaning of our work here? It means that the RAM, 1 mole of P, weighs 55.3981 grams, and it requires this number of coulombs to be deposited. Indeed, the mass deposited of 1 mole is 55.39, and that is the RAM of metal P. With that, viewers, we come to the end of our lesson today. I would kindly request you to work on more questions in this topic in terms of the calculations so that your mastery is attained. Remember to subscribe to the channel. We are at, I'll put it here, the material is available on YouTube at Steel Guitar 3660, all in small caps. So on YouTube, you can search for us at Steel Guitar 3660. Once more, we shall use this as a platform, and this material will also be found in our upcoming website. Let's keep on connecting. Comment on what you'd like us to improve on the video and how you found our lesson. Thank you, and God bless you.